things in black ink.
Yeah, ma'am. The last thing we did was T is equal to mg sine theta.
Is equal to, okay.
Sorry,
Now
ma'am.
whatever is written in black, you need to write, right, boss?
Yes, ma'am.
Okay, just start doing this. So the restoring force is provided by mg, the component of the weight of the bob, that is mg sine theta. Then we'll consider that theta is small. So whenever the angle is small, then sine theta approximately becomes equal to theta. Even tan theta approximately becomes equal to theta. You would have learnt in maths, right, boss, how theta, sine theta approximates to theta. Binomial expansions you would have learnt.
Ma'am, binomial expansions was out of the portion this year.
So you don't have that in mathematics.
No, ma'am, we don't.
Fine. Now we have to substitute for theta. Because here x becomes the arc length, L becomes the radius, say, of a circular path, theta is the angle subtended by the radius vector. So you very well know theta becomes equal to x upon L. Fine, boys?
Ma'am, like if theta is small, like that's if theta is less than 90.
Always. If theta is small, sine theta becomes theta itself. Tan theta also becomes equal to approximately, it approximates to theta.
All right, ma'am.
Because the higher powers will be neglected. You didn't study anything about anything in binomial expansion?
No,
Nothing you have studied? Oh. Okay, it goes under that concept. Anyway, theta is equal to, now we'll substitute for the force. Shall I go for the next slide?
Okay, ma'am. Sure.
I think I'll start. So now we need to substitute for f. F becomes equal to what will be the value? Mg, m into g divided by what was theta? X upon L? Yes or no, boys?
X upon L.
Okay. Oh, fine. X is the displacement. F is the restoring force. So I have to put a negative sign over here because the restoring force and the displacement are opposite to each other. When the body gets displaced, right, from the position of rest to say from position of rest to a extreme position, your restoring force will always act in the opposite direction. So both displacement and displacement and restoring forces are opposite to each other. So I'm bringing the negative sign over here. So then, according to Newton's second law of motion, F is m into A minus mg x upon L. So m and m will get cancelled. A becomes minus g x by L. X is a variable because the displacement keeps changing. The acceleration due to gravity and the length of the pendulum remains a constant. So I can put this minus g by L into x. Let me put omega square is equal to g upon L. Because if you need to understand why is that we are taking omega squared, not omega squared. Have you learnt about first order differential equation? You know what is first order differential equation? Okay. V is
No, ma'am.
equal to dx by, okay, V is equal to dx by dt. Second order differential equation, A becomes dV by dt, or I can write this as d squared x by dt squared. You haven't
Ma'am,
learned this?
differentiated
No.
2 times x.
Second order differential, yes?
We
You
haven't
haven't
heard of
learned.
that term, no.
But you have done this, d squared x by dt squared.
We haven't like used a square. No, ma'am. But we've done
No,
derivative.
you haven't. Okay, derivatives only dx by dt, that's it, right, boys?
Yes, ma'am.
Not beyond that you haven't done in maths. So
No.
the thing is that, yes, boys, the thing is that you should go for the second order differential equation. There you have to go for what we call it as a solution of the equation. So when you deal with all these things, you'll understand why omega squared is taken as g upon L. Right? Sometimes what happens is grade 12 mathematics concept, sometimes it happens that it is introduced in grade 11 physics in CBSE. So most of the time we try to explain, but if it goes beyond our syllabus of physics, we just tell that like omega squared is equal to g by L. Let us see, boys, once we'll complete our portions, if time permits, let me go for the second order differential equation if time permits. Right now you can go for this. So, or I can write omega is a constant, that's the angular frequency. A is inversely proportional to minus x. Always happens in CBSE. What you learn in grade 12 in maths will be applicable in grade 11 physics. So A is proportional to minus x, which means this type of motion is said to be simple harmonic motion. There are two conditions for simple harmonic motion. Your restoring force should be proportional to negative of your displacement, or the acceleration should be proportional to negative of your displacement. Hence, the motion is simple harmonic in nature. SHL. So next one is the time period of a simple pendulum. Time period. Now time period of a simple pendulum, T is equal to 2 pi by omega. But you very well know what is omega squared is equal to G upon L. Omega becomes equal to root of G by L. So here it is, T becomes equal to 2 pi root of L by G. This is a time period of a simple pendulum. This depends on the length of the pendulum and it depends upon the acceleration due to gravity. It is not going to depend on the mass of the simple pendulum. That is the reason, even if the mass of the pendulum is going to change, the time period will not change unless and until the experimental condition as well as the length of the pendulum is going to be a constant. Hence, the time period is independent of this.
Omega is also a constant in
Yes,
this
yes.
SHL.
Correct. Hence, time period of a simple pendulum is independent of mass. Was waves you will have certain topics because even there the CBSE has deleted some of the topics. So might be by end of Jan we'll finish waves. Then in case of the other three chapters, kinetic theory of gases, thermodynamics and thermal properties, only those topics which are not overlapping with chemistry will be tested on. Okay? Because there are certain topics which overlaps with chemistry. You would have already done in chemistry, so those topics will not be tested. Is that clear, boys?
Okay, ma'am.
Yes, ma'am.
We'll give you the portions for all those three chapters. So that already the portion is reduced one. There also we'll see wherever you're learning in chemistry, we don't overlap that with physics so that you will not have much burden of learning. Have you completed this, boys?
Ma'am, for what?
Now, suppose thermodynamics, first law of thermodynamics, second law, you all have learned those laws in chemistry.
Yes, ma'am.
Yes,
Certain
yes.
certain terminologies will introduce, will go according to it. Only thing is that what you have not learned is, you have learned isothermal process, adiabatic process. The work done in an isothermal process, the work done in adiabatic process, we'll do, because those are the basics of when you learn about your heat engines. Heat engines, you know, automobiles, you have heat engines, same thing. You have the heat engine working in the reverse way in refrigerators, how refrigerators work, right? Refrigerator works based on which principle? You have three laws of thermodynamics: first, second, zeroth, first and second. You're reversing the process in
Ma'am, is it the first?
refrigerators. Yes. So when we reach those chapters, we'll discuss boys. This is over. For simple pendulum, this is what you need to prove. Have you completed, boys? Because one more derivation is left. Then as per the theory part, your chapter gets over. Only what we need to introduce is a concept, what we call it as resonance. Now, resonance is very, very, very important. Otherwise, you cannot catch a signal. You know, all your receiving system, right? All your receivers, what you use in your automobiles when you want to receive a particular signal which is being broadcasted from your radio stations, you need to have a receiver. Basically, a receiver is a series LCR circuit. You know about capacitors, you know about resistors. You will be introduced to inductance coil in grade 12. Still, you should know. There we have electrical resonance. Here you will be, the resonance can happen in acoustics. The resonance can happen in your electrical resonance. The electrical resonance is the basic one where all your receiving sets, receivers will have. Okay,
Ma'am,
boss? Yes.
This year for 11th, we have any practicals for physics now in this.
No practicals for physics. Boys, if at all any practicals as such we have, it might be an MCQ based on whatever you have learned in O labs. We will confirm it.
Okay, ma'am. Ma'am, like, are there any new portions left, or only what we've learned so far?
No, because I think because of time constraint, whatever practicals, whatever we have done till O lab session, we'll do that, because now the lab is being occupied by grade 12, because they are facing the board exam.
All right, ma'am. Thank you.
Shall I move for the next one? Only one thing is left for me, boss.
Yes, ma'am.
Just right, boys. Oscillations of a loaded spring. Next subdivision, oscillations of a loaded spring. Look at this, boys. So suppose, let us consider, the question is, find the time period of a vertical oscillations of a massless loaded spring. You are loading a spring, say the spring, you make the spring to undergo oscillations. Then you need to find the time period of the oscillation, and you have to prove that this time period is independent of acceleration due to gravity. For that, let us consider a spring. The mass of the spring is negligible. One end of the spring is attached to a rigid support. The other end is left free. Now, this state of your spring, the spring is in a relaxed state, right, boss? The spring is in a relaxed state and it is at rest. Equilibrium means what? It is at rest. Next, what we'll do is we'll apply a mass or a block, we'll attach a block at the other end of your free end of your spring, so that now the spring will undergo a displacement. Let the displacement be equal to D. You clear, boys? The free end of your spring, you're attaching a block, so that because of the weight of the block, the spring is undergoing an extension D, but still the spring is at rest. Now this configuration, we call it as stretched equilibrium. Was in the first case, your spring is relaxed. There is no tension acting along the spring. The spring is relaxed and it is at rest. We call it relaxed equilibrium. Next case, you're applying a load at the other end of the spring, that is free end of the spring. So naturally the spring will get extended in the downward direction. It moves, say, to a distance of D, but still the spring is at rest. So such condition, we call it as stretched equilibrium. Now, since it is at equilibrium, when a body is at equilibrium, it means the total force acting in the upward direction must be equal to the total force acting in the downward direction. So what is the force that is going to act in the downward direction here? Can someone tell me what is the force that is acting in the downward direction here? This is M into G. Okay. And what is the force that is going to act in the upward direction? That will be your restoring force. The force which doesn't want the spring to extend. Right? The general formula for your restoring force will be F is equal to K into X displacement. Since we are taking only the magnitude of the restoring force, here your restoring force will be equal to K, spring constant. What is the extension? D. Is that clear, boys? So since the spring is under equilibrium, both these forces should be equal in magnitude but acting opposite in direction. So what happens? M into G becomes equal to K into D. Note down this, boys. Mark this as equation 1. The theory part is there, that I'll put it as your. I'll put
We
this
have to
part.
draw all these diagrams.
Yeah, both the diagrams. Or
Ma'am,
shall I, boys, shall I move on so that later on will you copy? So it takes time for me to come. Is that clear, boys? Is this part clear for you all?
Ma'am, like why did you remove the minus sign for restoring
No,
force?
I'm taking only the magnitude. Okay, let me go
Okay.
for the magnitude. I'm going for the magnitude. It's not the direction, it's the magnitude.
Ma'am, what's the subtopic? Okay.
Oscillation of vertical oscillations of loaded spring. Shall I write? Vertical oscillations. There can be horizontal oscillation also. Vertical oscillation of a loaded spring. Now still the spring is at rest. It's still not oscillating. Now let us make the spring to oscillate and find what is the net force acting on it. So I'm
Ma'am,
just moving on. Yes,
later
please.
on, we should draw the 3 diagrams, right?
Correct.
Okay. Okay.
Now look at this. Now what are you going to do next? Now what you are going to do is that you are going to apply a force on the block.
Ma'am,
There is a block attached. Yes.
ma'am, can you show the previous slide? I'll take a screenshot.
No, don't worry, boys. I'll put this in the.
Okay, ma'am.
The next case is that, boys, what you're going to make the spring to oscillate. For that, you are pulling down the block. You're applying a force in the downward direction. You pull the block down so that your spring now, your spring is now undergoing an extension of D plus X. Are you clear, boys? Right? You're going to pull the block by applying a force so that your spring undergoes an total extension of D plus X. And now you're going to leave the force, right? You leave the force in that sense. You're going to leave the block so that the applied force vanishes. So once you leave the block. Now the block will oscillate about the mean position. It goes d plus x meter above the mean position. Mean position is the position of rest. It comes to d plus x below the mean position. Now it begins to oscillate. Are you clear? Can you imagine? You have a loaded spring. You apply a force on the block, pull the block in the downward direction so that the spring undergoes a total displacement of d plus x. Now you leave the block. So now the block will move above the mean position. It goes d plus x meters above, it comes d plus x meters below the mean position. It begins to oscillate. So when a body is oscillating, which means when the body is moving, there should be a net force acting on the body. So what is the resultant force acting on the body? One is the force which is acting in the downward direction. You have applied a force, right? That will be equal to, sorry. So now the spring is oscillating. When the spring is oscillating, which means the spring is in motion, whenever a body is in motion, there should be a net force acting on the body. When the body is at rest, the force acting on the body will be zero. Now the spring is keeping on oscillating about its mean position. In that sense, there should be a resultant force acting on the body. So the force which is going to act in the downward direction is m into g. The restoring force which is going to act in the upward direction minus k into, because restoring force is, sorry, your restoring force F is equal to, the general expression will be k into x. X is the displacement. Here x becomes equal to d plus x. So your was m, if mg is equal to k into d plus x, will the body move? If mg is equal to the restoring force, as what we have seen in the previous case, the body will not move, boys. The body will not move if both the forces, restoring forces and the weight of the body acting in the downward direction, are balancing each other. The body will not oscillate. The body will only oscillate when the downward force is slightly greater than the restoring force. So that is why the restoring force here, what is the displacement? Here the displacement, total displacement is d plus x. So that's why you have a negative sign taken into consideration. So now F becomes equal to, the restoring force becomes equal to minus k into x. If the restoring force becomes equal to minus k into x, or if your restoring force is becoming directly proportional to the negative of the displacement, then all such oscillations, we term this oscillation as simple harmonic motion oscillations.
Ma'am.
Yes.
Ma'am, in the d plus x, what is d, ma'am?
D, okay, D was, see, when in the previous case, when you applied the mass, the spring has undergone an extension D, already D was there.
Yes, ma'am. Okay.
And now you're still pulling it down. Say you pull it down by a distance of x meters and then you leave. So now the total extension becomes D plus x.
All right,
Yeah?
ma'am.
So now you got F is equal to minus K into X. So I'm substituting for your force M into A is equal to minus KX, or A becomes equal to minus K by M into X, or A is equal to, I'll just take K by M as omega squared. So omega is a constant, A is proportional to negative of displacement. If this is the case, then the motion is said to be simple harmonic. Right, boss? Then the time period T is equal to 2 pi by omega. Omega squared is K by M. So then if you take the reciprocal, it is root of M by K. So here the time period doesn't have any factor which is related to G, that is acceleration due to gravity. Fine. So all the theoretical part of this chapter is over. Only you should know the qualitative idea of what we call it as forced oscillation, damped oscillation, and resonance. That is only the basic knowledge you need to know. Clear, boys?
Yes, ma'am.
Must keep learning. So what I could suggest for you all is that today evening you learn displacement, velocity, acceleration.